let's talk about methods of proof. Now, just as a remark, I'm not going to be talking about elementary forms of logic per se. So I'm not going to be talking about propositional logic here or other types of classic logics. I'll just sort of assume a general understanding of how logic works. And a lot of the big ideas I'm going to show you should make clear sense. They aren't going to be something that's going to come out of left field. At first, if you've never seen these ideas, you probably should have at some point. If not, sit back and just enjoy the fun, okay? Everybody's welcome here. So, there are two main kinds of mathematical statements that I want you to be aware of. So, mathematical statements of truth are quantified by universal. Now, if you're not familiar with what the word universal means, just think of it as for every, or for all. So if you ever see statements like that, I'm talking about universal, universal, and existential. So these are things like there exists, or there's at least one. That's very often when you see existential. As existential quantifiers. So if I give you some statement, which will be either true or false, they'll be quantified by things like universal and existential quantifiers. So words that look like these, which do have symbolic counterparts, but you might see them a little later on. I'm not quite sure. Which form the basis of proof writing and mathematical arguments. So just something I want you to keep in mind, just to remind you of what these words might mean in this context. When somebody sort of melted, that somebody writes for all x in D, this means in, this symbol here, in, where D is some collection, example, a set, then say X has a property. Say X has a property. That property is true for all X in D, or for every, whichever you'd like to phrase it like that. That's what universal, whenever you see somebody says for all, a universal statement. When somebody writes for some, notice the change of language here, for some X in D, and says X has property, has some property. I'm being kind of open-ended here. Has some property. It doesn't mean that it's that every one of the x's in D have this property, it means that at least one x of D has the property. You know it exists, hence the existential part of this. So it means it exists. So that's universal, that's existential. Now, I want to point out something that's very important. It's going to come up later. The logical negation of a universal statement is an existential statement. And vice versa. So that's something I really want you to really pay attention to. Now, I have it here in my notes, but I'm just going to kind of walk you through this idea. Okay, so if I imagine I give you a universal statement, and I tell you it's false, how would you tell me that it's false? What would you do? Now, at first sight, what you would tell me is that if I told you that every one of my friends is wearing a red shirt, and I told you, no, one of your friends isn't wearing a red shirt, right? That's naturally what you would say to somebody if somebody declared that all your friends were wearing a red shirt, just as an example. Right? But what does that mean? It means if I can point out a friend of yours that isn't wearing a red shirt, would you agree with me that that's an existential statement, right? It means that there's at least one of them that doesn't have the property. But what is not having a property? It's a property, right? So that's why if I want to negate a universal statement, I end up with existential statement. And likewise, if I have an existential statement, I say there's at least one object with a property. Say I have one of my friends that at least one of them's wearing a red shirt. What would you need to do to show me that there is nobody with a red shirt? I would check each one of them and tell you that no, there isn't such a thing, right? But what is that? That's a universal statement. But what is the universal statement? It's me saying, for every one of my friends, all of them aren't wearing red shirts, right? That's why the logical negation of a universal statement is an existential one and vice versa. Is that clear? So when you give me a universal statement and I say, like, no, yours is wrong, and you present a negation of that, it isn't another universal statement, at least when we talk about a single quantifier like this. You can build more complicated statements with quantifiers like these, and in combination, when you negate one, it flips the quantifiers from universal to existential, and vice versa. But notice that the property, in fact, flips as well. I'll let you think about that. I just want to keep things at high level here. So don't worry if that seemed a little bit daunting. I'm not going to go full-blown symbolic with this. I just want to give you the intuition. Keep things nice and simple. So in your studies, you will encounter probably multiple quantifiers. For example, if we're looking at, say, big O notation, you'll encounter existential statements with multiple quantifiers. But once you understand what the quantifiers mean, it's really not that bad. Okay. So I'm going to talk about a variety of different approaches you can to prove claims. So I just want to give you a flavor for what kind of statements usually mathematicians and computer scientists and other people that are interested in mathematical statements tend to make, so that I could talk about different kinds of proofs. So I'm not going to talk about every single type of proof out there. that's just not happening. Instead, what I'm going to do is I'm going to kind of categorize different styles of proofs. First, I'm going to talk about direct proof. I'll spend a little bit of time with this. So many claims that people make are universal claims. So many claims made are universal statements. Now, there are some standard ways you can prove universal statements. There are standard ways to prove such claims. So the first one, and this is one that you first encounter if you're studying logic, you'll encounter them in the form of truth tables and checking if forms are valid or invalid. You may have encountered this before, you may not have, that's okay. It's called the method of exhaustion. Or at least I'll call it that, because it's very intuitive. What you do is you consider all possible cases, then prove that, then something's wrong with that, then prove each case is true, or break the statement into cases. And then, of course, with each one of these cases, you would prove each is true. And prove each true. So you might naturally say, Dan, the method of exhaustion, imagine I give you some statement over a domain. That's what D is. If I'm talking about D, sometimes people call that the domain of interest or concern, or discourse, the domain of discourse sometimes. It's just, think of domain. It's like a set of numbers, for example, or if I give you some structure like a graph or some other mathematical object, I'm referring to something like a set. It could be, it's some sort of collection or something of that nature. Anyways, the thing that I would like to talk about here is that notice that the method of exhaustion, the first flavor of it requires me to be able to enumerate all of them, which doesn't seem very clear how to do that if you have an infinite number of them. Now, there's maybe some ways you can do that. I'm not going to focus on those, but you might know quite clearly if you're talking about basic forms of logic, like if you're talking about operators such as over truth tables, those will have, say, for example, exponential numbers of statements that you will check each one, and you can evaluate them based on truth values. So this would be an example of a method of exhaustion. If you want to check or prove that a certain logical form is valid, you would exhaust all possible cases of truth assignments and you would check them. That's an example of method of exhaustion. But you'll notice that I can do this over a finite formula of logic. Now, this may not, it's generally a technique that only has its reservations for certain things. The second part here is actually the one that's more interesting, at least in my opinion, is that I give you a statement and I can see that I can break or decompose the statement into multiple cases, and then I could prove each case separately. And if I cover all of my bounds on each case, so if I break it and I split all of my cases into two, like I have a domain, for example, if it was a domain on integers, say positive integers, every positive integer is either even or odd. If you think about it, you can prove this if you like. We're actually going to do something quite like that in a moment. You would agree with me that that's a possibility, right? Well, there's two possible cases there. If I show them for even and then I show them for odd, I've shown them for all the integers, right? That's what a good example of this. Okay? So that's a proof by cases or division of cases. The other one, and this is the one that you're going to find very often when we deal with direct proof, is suppose an arbitrarily chosen X in D, like above, like over there, and it satisfies the property. So your idea is that I give you X and D, and your job is to then prove it has the property, but you can't make any special assumptions about X. It has to be any one of the X's in D. Okay? So you would start off by supposing you have one of these, and your job is to deduce that X has the property. Sorry, I'm getting really excited here. So the big summary point I want to make is that in a direct proof, so this isn't a part of the second bullet, but it's closely related. In a direct proof, the idea is to show the property claimed to be true. Property claimed is true using previously established results. Previously established results and or observations that can be made via rules of logical inference. That N on that inference is a little funky. So the big thing here is that you either have a claim that you already have proven before, or you deduce more things from logical inference based on what you're given. So you might observe a certain property that occurs for the thing you're trying to prove. This is very often the case when you deal with algorithms, for example. You might observe a property that the algorithm has. You might prove this property, and you might use it to prove something else. So that being said, I'm going to give some examples of some proofs. So let's do that. Okay. So first I'm going to prove an existential claim. You'll find that they're not going to be as interesting for at least this example, because I got to keep things simple. But I assure you that not every existential claim will be dead easy, but these ones will. Okay. So here's a claim. So I'm going to present a claim. Now, if this claim is true, we often call these theorems. If it's a theorem that is building to a larger one, we often call them lemmas. And if it's a theorem that comes as a direct consequence of a theorem, we call it a corollary. But I'll just call them claims here to keep it simple. Some people call these propositions, and that's fine too. So this is just an example of an existential claim I'm going to prove for you. Just going to show you how I can do a direct proof. So I'm going to say there exists. There's the keyword that you will see right away. That's an existential claim. There exists an even integer. N such that it is the sum of two distinct prime numbers. So two distinct prime numbers. Now, just to discern everything for you, just in case you're not familiar with an even number is, nor a prime number. An even number is an integer that can be written in the form of 2 times some other integer. A prime number has exactly 2 divisors, 1 and itself, where itself is another number that isn't 1. So something like 2, for example, is a prime number because its divisors are 1 and 2. 3 is another prime number. 5 is a prime number as well. Is 4 a prime number? No, because its divisors are 1, 2, and 4. Okay? Is 1 a prime number? No. It only has 1 divisor. 1. Okay, so let's prove this claim. Now remember what I said earlier. It's an existential claim. So it's a there exists, that means there's at least one. So all I have to do is show you that. So what's the game plan here? So I like to use the phrase the game plan because I like to think about the strategy for proving the claim. So I need to say what I'm going to do. So what would I need to do? I need to show you, all I have to do for this is show you one even integer that has this property, right? So I give you an even integer, you have to show me it has the property. So I'm going to let n equal 10, for example. And now I have to justify for you that this, in fact, is a prime number. Actually, no, it's not a prime number, right? Got to read this carefully. It's the sum of 2 distinct prime numbers. But what does that mean? It means that there are 2 different prime numbers, and when I add them, I get 10. That's my goal here. I just decided on 10. You might find another number that works for this, but I just decided on 10. Then observe that 10 is equal to 3 plus 7, where 3 and 7 are prime numbers. And 10 is even, as 10 is equal to 2 times 5. Remember, it's 2 times some other integer. Now I have to give a conclusion. Therefore, there exists such an n so that it is the sum of 2 distinct prime numbers. And I'm going to indicate the end of my proof with this box. This just tells me that I'm done demonstrating the claim. So if you ever see a box like that, that's what it means. it's marking the end of a proof. It means I've demonstrated the claim. I've set out the proof. Okay, so that's one example there. Let's do another example. So that was an existential claim. Let's do a universal claim. So we're going to prove a universal claim. I'm going to consider 2 integers, m and n. Now, z here, you can think of that as integer. So if you see the fancy blackboard z, that means integer. If both m and n are even, then m plus n is even. So that's what we're going to prove. So if I give you 2 even integers, then the sum of them is also going to be even. That's what I'm going to prove for you. So remember what I said? We're going to do number 2. So I'm going to suppose an arbitrarily chosen element of D. Now, remember, I have 2 numbers, so I'm going to arbitrarily assume M and N as even integers. So I'm just going to suppose M and N are even integer, are any, getting really excited here, are any even integers. Are any even integers. So what does that mean? Now, I want to show you a very powerful but important trick that you should be aware of from logic. It's called the existential instantiation. It's a fancy word for basically me saying, if there exists an existential quantifier within a definition, you can invoke that and give it a name. So if something has that property and it exists, you can give it a name. So that's the fancy name for existential instantiation. Fancy word. Fancy word. So, well, M and N are even. So there exists, so I'm going to give them names because they exist, right? I told you, remember, even numbers, what are they? They are integers of the form 2 times another integer. So that means that other integer has to exist, right? So I'm going to give that integer a name, the one that multiplied by 2. So there exists integers k and k prime such that m is equal to 2 times k and n is equal to 2 times k prime. So now watch this, watch this. All I need to do now is I need to just write them in a form that's really nice, right? Then, well, what does it mean if I add m and n? M plus n is equal to what? I'm going to substitute m and n for 2k and 2k prime, right? So I have 2k plus 2k prime, right? But what is that equal to? And 2k plus 2 times k prime is equal to, well, they have a common factor, right? I can factor that out. 2 times k plus k prime, right? Now I'm going to let t equal k plus k prime. Now, one little assumption I've made in my proof that you probably didn't catch on to, that I've made a presumption about, is that if I add 2 integers, I end up with another integer. So that I'm making, I know that as in fact a mathematical truth about integers. So I think that's perfectly safe to do. So if I have t and I assign it to be k plus k prime, what should t be? It's an integer, right? It's an integer. Then m plus n is equal to 2 times t, where t is an integer. Where t is an integer, right? Piece of cake. Therefore, are we done? Yeah, we're done, right? We just showed that m plus n is equal to 2 times another integer, but that's even, right? So let me just summarize that. Therefore, by the definition of even, m plus n is even. And we're done. Bam! We did it. Okay, so those are 2 examples, one with existential, one with universal. I'm going to show you an example of this proof by division of cases, because I promised I was going to, I mentioned it and I thought, well, that's kind of interesting to bring that up. So let's talk about that. This claim is going to look a little strange at first, but I assure you it is quite nice and simple. Here's the claim. Any two consecutive integers m and m plus 1 have opposite parity. So if you're wondering what I mean by this, so this is the example I was mentioning earlier. If I give you m and it's even, my claim is that m plus 1 is odd. And if I give you m is odd, then it should be that m plus 1 is even. That's the claim. For you, this might be an obvious thing, but in mathematics, we have to be careful. Obvious is not an excuse to not justify it, okay? So words like it is obvious or it's obvious are not really mathematically tenable terms if you want to justify for somebody that something is in fact true. Instead, you could explain it to them. So if it's not obvious, you can write it in words and explain it to them. Hopefully I'm clear about that. So let's prove this claim. So I'm going to show you how you can do this with this case-based approach. Let m be an arbitrary integer. Then m is either even or odd. Now, to be clear, somebody might say, Dan, technically this is a claim that you would still have to prove, but we know that this claim is actually true. I'm just going to assert this as a fact, but there is actually a theorem out there that you can use to actually prove this from number theory, but I'm not going to prove that for you. I'm sure for this audience, this should be it's clear, right? It's something that you can see quite quickly. Okay. So I'm going to decompose this into two cases because m is either going to be even or odd. So I'm going to have two cases. So case 1, m is going to be even. So m is even. In this case, what does that mean? How do I prove it when it's even? I would use the definition of what even is. I use existential instantiation to get a name for an integer because this will exist in this sense. In this case, m is equal to 2k for some integer k. There's some funky noises in the back. For some k. And so, what's m plus 1 then? If m is equal to 2 times k. What is it? M plus 1 is then equal to 2k plus 1. And is odd by definition. Hence, m is even, and m plus 1 is odd. So that's case 1. So notice that by decomposing this into two cases, I can make more assumptions about what m is. This is often a very handy technique. When you're trying to prove claims directly about algorithms, you'll very often find that you might need to use this decomposing into cases because there might be two possibilities that could happen during execution, for example. This is something that you should be aware of. Or at least I want to make you aware of that fact. Okay, so case 2. What's case 2? Now you're going to see this is nice and simple. I'm just going to assume m is odd now. Then m is going to be equal to 2 times k plus 1 for some k that's going to be an integer. So what am I going to do? I'm just going to see what happens when I add 1 to it. So m plus 1 is equal to 2 times k plus 1, which is, of course, going to be what? What is it? Well, this is 2k plus 1, which is 2k plus 2, right? 2k plus 2 is, so 2k plus 2. You'll notice there's a common factor of 2 here. So I'm going to factor that out. End up with 2 times k plus 1. Notice k plus 1 is an integer. It's an integer. So what does that mean? So 2 times k plus 1 is what? It's even. It's 2 times some integer. Right? It's nice and simple. Is even. And boom, there you go. And now we need to conclude. We have to conclude our statement here. So now we've considered the 2 cases. Therefore, regardless that's we'll say regardless. It's sort of melted. Regardless of the parity of m, integers m and m plus 1 have opposite parity. And we're done. We've proven the claim. So notice how useful when we decompose it into cases, we can make more assumptions about what m is, but we rely on the fact that we've decomposed it into a complete listing of all the possible cases. So notice that I couldn't just prove this part. I have to prove that it's even or odd. So as a remark, I want to talk about how you disprove a universal statement. Now, remember, I talked about this actually earlier. I talked about with the example of somebody wearing a red shirt. So we're going to talk briefly about how do you disprove a universal claim. So what did I do in that example I mentioned? I pointed, if somebody claimed to me that all my friends were wearing a red shirt, I would point out one of them that was not wearing a red shirt. We have a special name for doing this. To disprove a universal statement, this would be what we would call a counterexample. So I present you a universal claim. Your job is to refute it by presenting a single counterexample. So to disprove universal claims, you must present some counterexample. So you have to present at least one counterexample. So counterexample. That is, show there is at least one x in my domain that does not have the property. Okay, so what does that mean? So I'm going to give you an example. just to illustrate this idea. So I'll give you a statement. So remember, if it seems really complicated, it's really not. Don't worry. All I'm saying is, if somebody tells you all your friends are wearing red shirts, and you know for a fact that they aren't, all you have to do to demonstrate to somebody that that not everybody's wearing a red shirt, you just point at one of your friends and say, hey, he's wearing a blue shirt. So imagine I give you a claim like this for all x, y that are real numbers. If x squared is equal to y squared, then x is equal to y. So suppose I give you this claim here. Now, I can think about how I would prove it, but I can see that there's a problem with this. So what I'm going to do is I'm going to present a counterexample. Now, normally when you present a counterexample, you don't just present the counterexample itself. You present it and then you show that it doesn't have the property. So it isn't just like, oh yeah, this is the thing and that's it. You notice that for example, my existential direct proof that I did earlier, I actually presented to you an example. I have at least one with the property, and I explained to you why it was that thing. It had that property. Same idea here. So I'm going to let x be equal to 1 and y equal to -1. So this is going to be an instance of my counterexample. So these are x and y. Those are x and y in the claim. And I'm going to check that these work to refute the claim. Then x squared is equal to 1 squared, which is equal to 1. And y squared is equal to 1 squared, which is equal to 1. So x squared is equal to y squared, right? 1 is equal to 1, right? Trivially. It's identity. But what does that mean? But x is not equal to y, right? See, 1 and -1 here. Since 1 is not equal to -1, therefore the given statement is false. Since I'm not proving anything, I don't usually put the box there. I'm not proving anything. I'm just refuting a claim. So that's really all I have to say about direct proofs. So hopefully you had a little bit of fun with this. This is some fun number theoretic examples. The next technique I'm going to show you is the so-called indirect proof. So in a direct proof, what I did was I used observations or previously established results, usually following from definitions, for example, or observations I can make about the structure of an object to conclude or infer logically claims. In this, you're going to notice that the name indirect, so I'm going to be talking about indirect proofs. I'm going to be showing you one such example of an indirect proof. This is not the only one, but this is most certainly going to be one that you're going to encounter in your study. So one thing I need you to note is that statements in logic are either true or false. So we're restricting ourselves to statements that look like this. Either you can say it's true or it's false. That's what a statement will be in the context we're talking about, okay? We're not talking about ambiguous things. We're talking about very clearly defined terms, clearly defined statements, and we're only restricting ourselves to statements that are either true or false, okay? So if you don't have a logic background, don't worry. Just follow the big ideas. So I'm going to change that period to a comma. So we're going to use this. So I'm going to show you one technique of indirect proof. It's so-called the proof by contradiction. So I'm going to give you a sketch of what a proof by contradiction looks like. It's going to work like this. Now, I should point out that a contradiction is a statement that is it's false for any truth assignment. So if I give you statements that are like, okay, I give you true and true for two valuations of a statement, it's going to be false all the time. This is in contrast to a tautology, which is a statement that is always true, regardless of the truth assignments of a logical form that I decide the sentence is going to be. Anyways, I'm not going to worry too much about the logic side of this. I just want to give you an idea of this. So a contradiction is definitely a statement that's always going to be false. That's the big idea here. So I'm going to be trying to derive a contradiction. So I'm going to make a bunch of nonsense. So the first thing you're going to do in such a proof is you're going to suppose that the negation of the statement is true. So we're going to start by just supposing or assuming that the negation of the statement is true. So if I have a universal statement, I'll make an existential statement. If I have something else, I flip the logic. Basically, I just get a negation of it. So I just presume that the thing that it isn't is in fact true. So the negation of it. Why? So if I'm trying to prove that the original statement is true, if I can do that, if I suppose the negation and I show that there's actually a contradiction, if I do that, that means it's going to be false for any assignment of the logic. That means that the original statement has to be true, right? So because statements are either true or false. That's at least the idea. So we're going to show this assumption or supposition if you really don't like assumptions. Leads logically to a contradiction. So a statement that's always false. Then you just conclude that the statement to be proved is true. So the whole idea is you start off by assuming the negation of the thing you want to prove, the statement. Then what you're going to do is you're going to follow the line of reasoning from that. So you're usually going to invoke definitions or a property that you might want to use based on the assumption of the negation. And by doing that, you're going to try to construct something that makes absolutely no sense or something that could never happen. Or it violates the original assumption, just in simple terms. So if we violate the original statement, that means that it and the negation clearly can't coexist with one another of the assumption. Anyways, I'm going to stop saying too many more things. I just want to get us right to the meat and potatoes of this. Like I'm saying, there's a lot of ways you can yield a contradiction. So let's do an example. There is no integer that is both even and odd. I told you I was going to give you some weird statement that you would think would be kind of obvious. So here's the claim. There is no integer that is both even and odd. So what do we do based on this sketch? So if I'm saying there is no integer, that means like there is no such thing, right? That means it's a universal statement. So what does that mean? It means I'm going to negate the statement and I get an existential statement. But what is the existential statement? Is that it has the property that it's both even and odd, right? That is, let's suppose not. Just for those that like suppositions over assumptions. I often like to write assume otherwise, but just for the sake of things, I'll say suppose not. For those that like suppositions. Suppose not. And then what you do is you elaborate on this. Suppose not. That is, suppose there exists n, which is an integer, right? That is both even and odd. That is both even and odd. It follows that both of the following properties hold. Now remember, n is both even and odd, so I'm going to just use what I did before in my previous examples. I used an existential I'm getting really excited. I used an existential instantiation to create two names, and I'm going to use them to try to derive a contradiction. So watch this. Watch this. So it follows that both n is equal to 2a for some a, which is going to be an integer, n is equal to 2b plus 1 for some b, which is another integer, and the following. Now remember, n is an integer, right? So it can't be that like this equals something and then that equals a different thing. They have to be equal to one another because it's n, right? And that 2a is equal to 2b plus 1. That has to be true, right? Because it's n. N is equal to n. So remember, we know that n is equal to 2a, and n is also equal to 2b plus 1. So, as I mentioned on the previous board, we know that 2a is also equal to 2b plus 1, because n is equal to n, right? That's just identity. So I'm just going to simplify things down a little bit by simplifying this equation here. So by simplifying, we get 2a minus 2b is equal to 1, right? I'm just going to subtract off. I'm going to subtract both sides, 2b. And then this is true if and only if. This is abbreviation for if and only if. Some people also use the double arrows like this. If and only if 2 times a minus b is equal to 1. Now I can rearrange this, and a minus b is equal to 1/2. Now, one important property I already mentioned earlier about integers is that if you add two integers, you get an integer. As a byproduct of this, if you subtract two integers, you should also get an integer. So over there, that looks a little suspect over there. So let's see what happens. The difference of the difference A minus B, the difference A minus B must be integer. Must be integer. As A and B are integers, right? Are integers. However, A minus B is equal to 1/2. And 1/2 is not an integer. What is it? It's a rational number. It's not an integer. Therefore, A minus B is both an integer and not an integer. Which is a contradiction. And naturally, you would say, therefore, you would say a statement. But typically in contradiction proofs, the convention is that you don't normally write that after, because you just said what the contradiction is. And because it's a contradiction, it means that the original statement must be in fact true. Because if you take its negation and it leads you to a contradiction, remember, is a statement that's always false, then it means the original statement must be true. Okay? So that's why we call it an indirect proof. Okay. Now it's worth noting that I'm not going to show and talk much about it, but there's another type of indirect proof called a proof. It's called proof by contraposition. This is another one that takes advantage of the form of a certain set of logic. So if you give me a statement, I can give you its contraposition or contrapositive, to be positive. Sorry, I'm getting a little excited. If I give you a statement involving a conditional, I can give you something called the contrapositive. I can take such statements and I can do some neat thing with them. I just want you to be aware that this exists. I'm not going to do any examples with it because it's a little bit more technical. I think that this is more intuitive to talk about. Just remember, the big idea with proof by contradiction is that I assume or suppose the negation of the statement, and then I try to show that the statement yields a contradiction. Now, it doesn't have to be as garbage or contradictory as this thing, but it might be that it violates the assumptions that you start off with, for example. In an algorithm, this is quite common. So, for example, you might end up having something where you're supposing that you have an answer that an algorithm outputs, but you assume that it doesn't actually do that, so there must exist another answer that pops out of your algorithm. And what you do is you follow through properties that your algorithm has, and you can show that you can take such an answer, you can actually constantly improve it, so you actually get an answer that looks exactly like the one the algorithm gives you. But if you suppose it didn't exist, you suppose it exists and it's better, but your algorithm's able to build one out of the answer, then it must be that the algorithm produces it, hence a contradiction, and so on. So this is actually something that does pop up when you do analysis of algorithms and you try to prove the correctness of some algorithms. This typically pops up, this structure I just talked about, pops up oftentimes when we deal with optimization problems. But I'm not going to go into too much detail there. Clearly I get really excited, so I'm going to avoid doing that because I got to keep things ground and pounded in mathematical, that dreaded M word, the mayonnaise, okay?